You're on a construction site. The concrete truck arrives, but the mix looks too stiff to pump or place easily. A worker grabs a hose and starts adding water. At that moment, with that single action, the structural integrity of your concrete has been permanently and irrevocably compromised. This is not an exaggeration. It is the direct result of violating the most fundamental law of concrete technology, the water-cement ratio. This single number is the master variable that controls nearly every aspect of your concrete's performance, from its ultimate strength to its lifespan. So, what is this magical ratio, and why does it hold so much power? In this video, we're going deep on the water-cement ratio. We'll explain the chemistry behind it, bust the myth that wetter is better, and show you the right way to achieve workability without sacrificing strength. By the end, you will understand why controlling water is the most important job on any concrete site. Let's start with the fundamental science. What is hydration? Concrete doesn't dry to harden, it cures through a chemical reaction between cement powder and water, known as hydration. In this reaction, water molecules break down the cement compounds and form new, strong crystalline structures that bind the sand and aggregate together. This is a precise chemical process. The amount of water required for complete hydration of the cement particles is surprisingly low. Water-cement ratio of approximately 0.23 to 0.25 by weight. However, if you've ever seen a mix with a 0.25 ratio, you'd know it's a dry, unworkable heap, impossible to place or compact. So, we always add extra water to give the concrete the fluidity, or slump, needed for placement. This is where the critical trade-off happens. This extra water does not participate in the chemical reaction. After placement, it remains trapped in the concrete and eventually evaporates, leaving behind a complex network of microscopic pores and capillaries. And pores are weak points. The more water you add, the more pores you create, and the weaker and more permeable your concrete becomes. It's that simple. This relationship was quantified over a century ago by Duff Abrams, who established Abrams' law. It states that for a given combination of materials, the strength of concrete is determined only by the water-cement ratio, provided the mix is workable. This is a profound concept. It means that once your materials are chosen, strength is not about adding more cement, it's about controlling the water. The relationship is inverse and nonlinear. For example, reducing the water-cement ratio from 0.50 to 0.40 can increase the compressive strength by as much as 50%. This is why specifications are so strict. A common and catastrophic on-site mistake is to add water to increase slump without recording it or adjusting the mix design. You are not just making it easier to work with, you are mathematically downgrading the concrete's specified strength. A pro tip from concrete technologists is to always have a slump test kit on site and to reject any load where water has been added without authorization and recalculation by the site engineer. So, if we can't add water, how do we make concrete workable enough to place our own dense rebar and into complex forms? The answer is chemical admixtures. Specifically water reducers and superplasticizers. High-range water reducers. Think of cement particles as tiny, jagged rocks that clump together, trapping water and resisting flow. Water reducers are surfactants. They coat these particles, giving them a negative electrical charge that causes them to repel each other. This repulsion breaks apart the clumps, releasing the trapped water and making the concrete fluid without adding a single extra drop of water. This allows you to achieve a low water-cement ratio for high strength while still having a highly workable, placeable mix. Superplasticizers are even more powerful, capable of creating a flowing, self-leveling concrete with a very low water-cement ratio. The efficient workflow secret is to order concrete with the correct slump for the task at hand and use admixtures to maintain that slump without compromising the WC ratio. The impact of the water-cement ratio extends far beyond 28-day compressive strength. It is the primary governor of durability. Concrete with a high water-cement ratio is like a sponge. Its interconnected pore network allows aggressive agents like chloride ions from de-icing salts or seawater and sulfates to easily penetrate the concrete. Once inside, Chlorides corrode the steel reinforcement, causing it to expand and spoil the concrete cover. Sulfates react with the cement paste, causing it to expand and disintegrate. A low water-cement ratio creates a dense, impermeable concrete that acts as a fortress, protecting the steel and the paste from these attacks, thereby ensuring a long service life. This is why key structural elements in harsh environments, like bridge decks and marine structures, have very low maximum water-cement ratios specified, often 0.4 or below. A common drafting mistake is to only specify the concrete grade, e.g. M30, without also specifying the maximum water-cement ratio, which is essential for guaranteeing long-term durability. To summarize the key takeaways: 1. The water-cement ratio is the mass of water divided by the mass of cement in the mix. 2. A lower ratio means stronger, denser, and more durable concrete because it leaves fewer water-filled pores after hydration. 3. Never add water on site to improve workability. It permanently and severely reduces strength. And 4. Use water-reducing admixtures to achieve workability at low water-cement ratios, which is the hallmark of modern, high-performance concrete. Now I want to hear from you in the comments below. What has been your biggest challenge in controlling the water-cement ratio on a project? Was it dealing with a stubborn batch plan, training a crew to stop reaching for the hose, or managing the effects of high temperatures on slump? Your real-world stories highlight the constant battle for quality control. If this deep dive into the most important number in concrete has been valuable, please give this video a like and subscribe.